How the Earth came by its moon has always been something of a mystery. Scientists had theorised that a Mars-sized planet called Theia crashed into the Earth and that the moon was formed from the debris. But analysis of the rock chemistry from the lunar surface reveals that the moon and Earth are practically identical. There appeared to be no chemical trace of this Theia, so where did it disappear to? This chemical conundrum has thrown a lot of doubt on the impact theory.
But this week, a series of papers in the journal Nature suggests that the theory still holds water. Using simulations and also isotope measurements, scientists have demonstrated that the similarities between the Earth's and the Moon's chemistry are not at odds with the impact theory, as Open University planetary scientist David Rothery explains.
Ever since we got the first data back from the Apollo missions, it's been thought generally that the Moon is a result of a giant impact, something about the size of the present Moon or a bit bigger, maybe Mars size, hitting the Earth, which was a glancing blow, if you will, and it threw a lot of debris off from the Earth, which coalesced together to form the Moon.
And this happened fairly early in the Earth's existence?
Pretty early in the Earth's existence, yes. I mean, the solar system was growing round about 4.56 billion years ago. And there'd be a series of giant impacts, all within a few million years of each other. And the last one that hit the Earth was the one that would have formed the Moon, if that theory works.
And this slew of papers that are in the journal Nature, what do they add to the story and how?
What they show is that the Moon and the Earth are too similar for the Moon forming impactor to have come from a very different part of the solar system. The Moon forming impactor has come from the same region of space that the Earth formed in.
And how did they reach that conclusion?
There's three papers. One of them is looking at the flavours of oxygen which are there. Oxygen comes in three sorts: oxygen 16, 17 and 18. So you've got normal oxygen, slightly heavier oxygen and even heavier oxygen. The ratio between these is quite a good way of fingerprinting material, because if the Earth and the Moon were very different in their oxygen isotope ratios, that would tell you they'd formed somewhere different.
So that's one of the papers.
That's one of the lines of evidence.
What are the other two?
The other two are dealing largely with tungsten. There's an isotope of tungsten, which is tungsten 182, which is produced by radioactive decay of hafnium-182. Hafnium is an element which likes to be inside rock, whereas tungsten likes to go inside iron. So when you're forming a planet, the tungsten will go and join the iron in the planet's core. But if you've got hafnium in the rock, that hafnium, after the core has formed, can still decay to produce some tungsten. So you'll have a tungsten enrichment in the rocky part of the planet, because that tungsten was held in the rocky part because it used to be hafnium. So it doesn't bear on how the Moon formed, it bears on when it formed, because it was all done by the time that all the hafnium had decayed.
And do they shed any light on whether the Moon is made of cheese in these three papers?
We did discover calcium on the Moon with an X-ray spectrometer on the Indian satellite Chandrayaan-1 that I was involved in. And calcium had never been detected from lunar orbit before. So, there's plenty of calcium in cheese. So we can't rule cheese out.
Food for thought then. That was David Rothery from the Open University.